This is Science Max, experiments at large. Science Max!
Well, hello there, Science Maximites. Today, we are going to be flying on Science Max Experiments at Large. Take a look at this. It's my paper airplane. Give her a bit of a throw and she flies amazing. Now, take a look at this. This one is lighter than air. It's a helium balloon, and guess what? It flies on its own. See you later. Well, just hold on a second there, friend. What's this whatchamacallit called? I'll tell you. It's called a hoop glider. Give it a toss and she flies really well. But today we're flying in a whole new way, Science Maximites. I know it sounds like we've covered all the bases for flying, but we haven't. Come on, follow me. Oh, didn't actually realize how much these goggles would fog up. Where was I? Oh, right, we're flying today on Science Max. Come on. Today, we're going to be building a tumble wing. That's a kind of paper airplane that flies on a cushion of air. This is a big mouth tumble wing. It doesn't look like much because, well, it's not. It's just 2 strips of paper taped at either end. But what you do is you throw it in the air and you walk along behind it with a hard surface like this, and that little scoop of air keeps it flying. And here's how you can make a tumble wing of your own. But first, a word about paper. Did you know that paper comes in different weights? The kind of paper you get from the printer is actually pretty heavy. The ideal paper to use for tumble wing making is from a phone book. You may not have a phone book at home. They're kind of rare right now, but its paper is very, very thin and the perfect for tumble wing flying. Now, if you don't have a phone book around, you can use newspaper. It works almost as well. What you do is you cut out some strips of paper, and you just need 2, and you put them on top of each other, and then you offset them, which means you take the top one and you slide it over till there's about maybe a centimeter, 2 centimeters, something like that. And then you take your handy dandy science tape, which is the same as regular tape, except you use this tape only for science, and you tape the edges very carefully like that, and flip it over to the other side. Make a little tape on this side, just like that, and there you go. You have a big mouth tumble wing. Now you also want to tweak it just like you do with a paper airplane. You want to curl the paper a little bit, curl this side a little bit, and let's see how it flies. You'll know you have it right when it doesn't go to the left or right, but just opens up and tumbles straight down. Ah, not too bad. That one curved a little bit, so I'll have to tweak it a little more. Now, the other thing you're gonna need is a nice hard surface. The kind of signs that you get when there's an election are perfect. I happen to have a few of these sitting around, and they are made of something called corrugated plastic. They're very light, but they're also very hard. So you can use this, but you can also use cardboard if you don't have any of these around. So what you wanna do is get your tumble wing and your hard surface and flip it in the air, get it flying very nicely, and then walk behind it with your board, and a scoop of air will be behind it, and it will fly. But it may look easy when I do it, but that's because I've been practicing quite a bit. So here are some tips for tumble wing flying.
Tumble wing flying tips. When flying your tumble wing, you want to be indoors, away from any wind or other kinds of moving air. A long hallway or a big room is best so you don't run out of space. The angle you hold your board is important. Too much tilt or too little and it won't work. Keeping your tumble wing in the air is mostly about the speed that you walk. Too fast and the tumble wing will go over the top. Too slow and it'll fall. Finally, practice, practice, practice. Happy tumble wing flying!
Now I just need an expert to help me. Okay, let's see here. Lisa from Logis Academy. She'd be perfect. Okay. And, oh wait, I need a lab coat. Oh, and Lisa needs a lab coat. There we go, Lisa's lab coat. Good, my lab coat. All right, my turn. Oh, my lab coat changed color again. I'll fix it later. Lisa's gonna be here any minute.
Oh!
Hey!
That was so fun!
Oh, did you like the portal?
I loved it! Hi, Phil!
Lisa from Logix Academy. I'm glad you're here. Your lab coat changed color as well, though. It's supposed to be yellow. I think we had a glitch.
I kind of like it, though, blue.
No, but we gotta do yellow. Yellow is the Science Max lab coat color.
Okay.
So, we are here to talk about the tumble wing. I've got my big mouth tumble wing here.
I have
Got
mine,
yours?
too. Yeah.
Now, what are we want to max it out, obviously. What else can we do?
Well, actually, there's a lot of different designs that we could try. This is a big mouth tumble wing. There's also tumble wings that are just a straight sort of single wing.
Oh.
And then there's some that are like an actual airplane or a glider.
Ooh, and we can max them all out.
Of course.
All right, let's get started.
Let's do it.
And we'll get the yellow lab coats.
And I really like the blue.
We gotta get the yellow. There, now we've got our yellow lab coats. I've got my big mouth tumble wing, and I got my board to push the air.
Oh, look at that! I voted for you.
You did?
I did.
Oh, you were the one. Okay, so let's talk about the science going on behind this air surfer.
Okay, so just like in an ocean, if you were surfing in an ocean, you'd be surfing on a wave of water. Right now, our tumble wing is surfing on a wave of air that you're creating with a board. And air and water are actually both fluids.
Oh, cool. So we
They
can.
behave the same way.
So it really is surfing.
It is surfing. And actually, sometimes we call those air surfers.
Cool. Well, why don't we have a surfing competition? Because I actually have here a Team Phil board and a Team Lisa board. Okay, so what do you want to have a race?
Yeah, absolutely.
Okay, you want to take this one? This one flies really well.
Definitely.
I'll make a new one.
Okay.
Welcome to the Air Surfing World Finals, almost live from Science Max headquarters. I'm Jim and I'm joined by Chuck. Today it's Team Phil versus Team Lisa.
Team Lisa has a lot of heart, Jim.
But Team Phil is on his home turf. Let's see how they do. Round one is, of course, the tumble wing race.
And a great day for air surfing. The teams are ready, and there they go.
Ooh, Team Lisa looks like she had some trouble starting. Team Phil has already pulled ahead, but Team Lisa is off the marks now.
I think that beginning fumble might have cost her.
Let's see. Team Phil with a commanding lead, but Team Lisa's catching up. Oh, Team Phil loses his tumble wing at the last minute. A great dodge and a pass by Team Lisa. Can she hold it? And no!
Taking 10 steps back is the rule when you drop your tumble wing, Jim. It's anybody's game.
Looks like Team Lisa fumbles her start. Phil pulls ahead. Can he be caught?
Almost at the finish.
Yes! Team Phil with the win. What an upset!
All right, you had a lot of practice with that one.
Yeah, okay, so you got another design?
Yeah, let's try the single wing
New
one.
design.
Okay.
So at the end of the first round, we have Team Phil with 1 point, Team Lisa with 0.
But now we go to the second round where the design changes. We're now looking at a single wing design. It still tumbles like the big mouth tumble wing, but made from a single wing.
Does that make them harder or easier to fly, Chuck?
A bit harder. They're faster and more maneuverable.
If you wanted to, you could research tumblewing, and you would be able to find this design. And this is what these show you where to fold it.
Yes. So the dotted lines or the dashed lines are where you would fold, and the solid lines is where you would cut.
What's more, Team Lisa has more practice with this version.
And they're off. Oh, Team Phil with another early lead, but Team Lisa's catching up.
Phil doesn't have much practice with this version, and it's starting to show.
You're right, Phil fumbles.
No.
Oh, Phil fumbles, and Lisa passes him for the win. There we go. At the break, we're all tied up with Team Phil and Team Lisa with 1 point
Look
each.
how well mine's going. This is an ornithopter. It's a machine that flies by flapping its wings. When people were still trying to figure out how to get something to fly, they thought, copy a bird. A bird flaps its wings and it flies, just like this. So, why don't we have airplanes that fly by flapping their wings? It turns out that flapping wings is actually complicated mechanically. First of all, you have to tilt the wing when you go up so it doesn't take as much air, and then turn it so you push more air on the downstroke. So flying like this would be kind of hard for an airplane and really hard to do on a large scale. So humans came up with this, a propeller. A propeller catches the air, and if you spin it fast enough, it gives you lift. So if you orient it upwards like a helicopter, it will give you lift, or if you orient it this way, it will give you thrust, just like an airplane. So that begs the question, why don't birds and insects use propellers to fly? Turns out, though, that rotating a propeller is really hard to do with something that has muscles and tendons. So in the end, birds fly by flapping their wings, and humans first learned to fly by rotating a propeller. Science.
Lisa and I are air surfing. We've tried 2 different versions of tumble wings, but now Lisa has a new design, one that doesn't spin as it flies.
Okay, so what do you have now?
Oh, check this out, Phil. This is a Mosquito glider.
All right, so it's like a paper airplane.
Yeah, but it's not made of paper. It's made of a light foam.
Ooh.
The Mosquito gliders work the same way as the tumble wings, but because they're much larger, they're much harder to control.
I got it. Oh, no, 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 no. Oh, almost into the stuff. Not bad though, right?
You got it.
This is very tiring.
This is really hard. It takes a lot of flying time to master.
We got the hang of it, but we quickly learned that you have to run a lot faster with the gliders. And we were soon out of breath.
Whoa, sorry. You gotta be in good shape for this.
Turns out a bigger glider is much harder to fly. So,
Ultra maxed out Mosquito glider.
we made it even bigger. Why? Well, because it's Science Max.
Bigger board.
We needed a much larger board and tried first with 2 people.
Ready? Going. Oh.
And then with 1. And the most we were able to get it to fly was not a lot. Our conclusion?
Large airplanes just don't fly very well.
Well, homemade ones.
But we can try something else.
Okay,
Let's try something else.
let's try something else.
Today only, I got a super special on anything that can fly. Go on, pick something out. Oh, you had the paper airplane. Oh, good choice. Good choice. But guess what? Paper airplanes don't fly. Full price. Yeah, I know, but before you start arguing with me, you need to know the difference between flying and gliding. A paper airplane does not fly, it glides. You need constant thrust in order to fly. If you do not have constant thrust, then you glide. Take this bird. This bird can fly because it flaps its wings. It has constant thrust. On sale. But this airplane cannot fly. You give it some initial thrust when you throw it, but after that, it can only glide. Full price. But look at this. It's an airplane powered by a propeller on an elastic. Now we're talking constant thrust. It can fly. On sale. But it can get confusing. I mean, look at this flying fish. Nope. Flying fish cannot fly. They can only glide. Full price. Look at this. It's a cute little flying squirrel. He climbs a tree, jumps off from a high branch, opens his legs, and there's a little flap of skin there that allows him to sail to another tree. Haha, flying squirrel. No, not flying, no constant thrust. Gliding squirrel. Full price. Okay, tell you what, you came all the way down here, I'll make you a deal. Check this out, flying fish, now it has a propeller, it has constant thrust, it flies for real. And ditto, squirrel with a jet engine, And now you know the difference. Something that flies has to have constant thrust, otherwise you're just gliding. Squirrel away! I forgot to gas him up.
Look at those clouds. Aren't they nice? Did you know there are different names for clouds? Like those clouds right there? Those are cumulus clouds. They're the kinds that look like cotton balls, really fluffy and light. Well, they're not exactly fluffy and light. First of all, they're not fluffy, they're wet. It would be sort of like being a very dense fog, and it'd be very wet if you were in that cloud. And they're also not light. In fact, they're not light at all. That cloud right there weighs about 500,000 kilograms. That's the same as 100 elephants. 100 elephants just floating around in the sky? Come on, how does it do that? It does that because it's so spread out. But water is very heavy. Interesting to think about. 100 elephants just floating around in the sky above our heads at all times. Almost makes you want to go inside.
Our air surfing tumble wings worked well, but our Mosquito gliders were a bit too maxed out to fly really well.
Large airplanes just don't fly very well.
Well, homemade ones.
But maybe we should try maxing out the tumble wing just to see what happens. So we did!
Okay, Lisa, I'm gonna throw it, and then you're gonna push the sign.
What?
Go! Wait.
Oh, did it go? What happened?
It didn't, whoa, it didn't work.
We tried it and tried it. And it turns out, yeah, it doesn't fly.
Go, 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 go! Go, go, wait.
But I mean, this is Science Max, so of course we had to at least try maxing it out.
Phil,
I don't know if this is working.
it's heavy.
It's very heavy. Okay, maybe we should go back to a slightly smaller version.
Sounds like a plan.
Okay.
High five?
High five. This is a boomerang. Boomerangs are from Australia, and the cool thing about boomerangs is when you throw them, they come back. With practice. That was close. When you throw them, they come back. And it comes back. Comes back. Come back. Come back. So, why does it come back?
Well, if you take a look, it's made of two wings, like airplane wings, but with one important difference. You see, a wing has a shape called an airfoil, and this gives lift. But check it out. The boomerang has one airfoil pointed this way and the other pointed the other way, which means if you spin it in the right direction, each wing will get lift as it rotates. But how does lift make it come back? Well, that's the trick. You see, you throw it sideways. The lift from the wings makes it go in a big circle and come back to you.
So when you throw a boomerang, this side starts to go this way and it gets a little bit of lift. Then this side gets a little bit more lift, and then this side gets lift, and each time it gets lift, it starts to turn just slightly. So as the boomerang spins, it describes a nice big arc in the sky and comes right back to you. Ha-ha! And that's how a boomerang works. Thanks, Phil. No problem, Phil. Hey, do you want to get lunch? Yeah, lunch sounds good. Okay, come on. Well, the Science Max headquarters has a nice cafeteria.
We've tried air surfers of all shapes and sizes. And what have we learned?
Maxing out an air surfer by making it bigger is really difficult.
Very difficult, yeah.
So what we've decided to do is go back to our original big mouth tumble wing and instead do it on a maxed out obstacle course!
Tumbling surfing round 3, the maxed out obstacle course. Let's take a look at the obstacles. The tree slalom, the podium ramp, the hanging hoop, ring walk, wall of boxes, ladder tunnel, side hoop, ball promenade, and the barrel run.
So here's how we play. I go through and then you follow me. And if you make it through an obstacle and your tumblewing's still in the air, you get a point. And at the end, we count how many points we have and we see who won.
And it looks like they're ready to start. Here we go!
Where are you, Team Lisa? Oh. Oh, yeah. Oh, no. Okay, what do I do with the boxes? What do I do with the boxes? Going through the boxes! Definitely didn't make that one. Recover! Ah! Oh. Okay, definitely lost a point there.
I'm almost there! Right behind you!
Yeah! Knock the barrels over, getting
I get an extra point for that.
Oh, yeah! Nicely done, high five.
Awesome.
See how the airflow from the board keeps the air surfer in the air? Well, the trick is to give it just the right amount of air to keep it in control. Not too fast and not too slow. That's the science to good tumblewing flying. So, with the points from the last round added up, Team Phil and Team Lisa are tied again!
You know what that means? Tiebreaker! Thanks very much for watching. watching Science Max Experiments at Large Tumble Wings. You want to go first?
I do. Let's do it.
Okay, you go first this time, and then I'll follow you. I think it's easier to go first. So, okay, ready?
Yeah.
Your mark, you set, go. Ha. Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large, and this is a syringe. You might know syringes from when you get a needle at the doctor, but syringes are used all the time in science because they let you measure very precise amounts of fluid. Now check it out. You push the plunger down, and it comes out the top. Or you could pull the plunger in, and it would suck more fluid in this way. But check this out. I've got a syringe attached to a hose here, and this hose is filled with water. And I wondered if the hose was really, really long, how hard would it be to push this plunger down? Of course, I don't know where the end of the hose is because it was really long and I had to string it all the way around, so, here it is. Okay, so let's find out. Push the syringe down and water will come out the other end of the hose. Pretty cool. You see, this is called hydraulics. Hydraulics is a branch of science that deals with fluids like water. But hydraulics are also a mechanism used in a lot of machines. Check this out. This is a syringe with a short hose on it, much shorter this time. And I press down on the plunger of the syringe and water comes out. And I pull in on the syringe and water goes back in. Because the plunger is airtight, it allows me to push or pull the water. But what if I close the system and take another syringe and attach it to the end of the hose like this? Well, then, if I push this plunger in, this syringe fills up with water. And then I pull this plunger out, the syringe empties. So check it out. This plunger raises and lowers based on what I'm doing with this plunger. And you know what that means? We've made a remote control. Huh? Check it out. So, if you take two syringes and you take a hose and you attach them to something you want to remote control, voila, you can build something like this. We have made our very own robotic arm that you can power remotely with hydraulics. Pretty cool, right? If you want to build one of these yourself, here are the materials you need.
First, you need two supports and the arm. I used pieces of wood, but you can use wooden spoons, rulers, or pencils. You'll need some craft sticks, elastics, and a paper plate. And of course, two syringes and a hose, which you can get in an art supply store or a hardware store.
Here's how you build your own hydraulically powered arm.
First, make the base by tracing holes for your supports the width of a craft stick apart. Cut out the holes and use a craft stick and elastic to secure the supports underneath the plate and on top. Then add some elastics and a piece of craft stick in the middle so the supports won't scrunch together.
Because we are holding this whole thing together with elastics.
Then get your syringe in there and keep it propped up with more elastics. Then get your arm and slot it in between the supports. The arm should be horizontal when the syringe is half full. Elastics to attach the arm and the syringe.
Then push down on this end of the plunger and, ha-ha, you have a remote-controlled robotic arm. You can also max it out even more by adding more degrees of movement. You can make the arm rotate side to side. You can even add a little claw attachment at the end and power it all using syringes. Haha, science and hydraulics. So let's max it out. I just need an expert to help me. Let's see. And over and that way. Oh, Chris from Logix Academy, of course. Logix Academy knows all about building robot stuff. I'm sure Chris can totally help me. Let's go. Come on.
Oh, hey, Phil.
Oh, hey, Chris from Logix Academy. Great to see you.
What took you so long?
How long was I gone?
And what's with the orange lab coat?
Oh, it happened again. It keeps changing the color of my lab coat, but this time, Chris, I prepared for it, and I wore another lab coat. See?
Blue?
No! Well, you know what? This is happening a lot, Chris. So I wore another lab coat under this lab coat. I'm gonna have to wear a lot of lab coats, though, because this is happening all the time. We should talk about hydraulics, right?
Okay, yes,
Yeah, because we
yes.
got some cool stuff planned. Okay, so we're just gonna get the table in here. Oh, okay. This is the hydraulic arm. Check it out.
Oh, very cool, very cool.
If we want to max it out, what can we do? We can make it bigger, we can make
What
an
if we
arm.
did it so that the force you put on this side gets multiplied so that this side's even stronger?
Ooh, what do you call that when that happens?
Force multiplier.
I like that. Force multiplier, it sounds like a video game. So we would have a lot more power.
You have a lot more power, which we can do fun stuff.
Yeah, so if we had like lots of power, what would we do? We'd like crush something.
Yeah, let's crush some stuff.
Yeah, we could crush some stuff. Okay, can we start with syringes though?
Yep.
And then we'll work up as we go.
I like it.
So what do we need? Do we need different sizes?
So yeah, I was thinking we need a small.
A delicious plate of cheese and crackers, my favorite snack. But these crackers are pretty salty, so I should probably pour myself a glass of water first, huh? No, my cheese and crackers! Why does this happen? Why does the water stick to the glass? Well, because of science. And the reason why it happens gets a little complicated, but it boils down to this one simple thing. Water likes to stick to things. Huh? Did you see? Did you see how it stuck? No, of course you didn't. You know why? Because it only sticks on a small scale. See those drops of water? That's water sticking to the surface. But it only works when the surface tension of the water is less than the force of gravity, which is why water drops fall when they get bigger. So it sticks to things. That still doesn't explain why you can pour water out of some containers without any drips, and other containers make it nearly impossible.
It's all about the angle. Water will flow very easily when there isn't a large change in direction, like around the curved top of this glass. But when there's a big change in direction, like at the mouth of this teapot, the water can't make that turn as easily. This is also why pouring from a full glass is much messier than one that's less full. Pouring out of a full glass, the water only needs to change direction this much to flow down the side. But from a half-full glass, the water would need to change direction this much.
So all this happens because water likes to stick to things. So let's do an experiment and coat this glass with hydrophobic spray. Now, hydrophobic coatings repel water. So if it's repelling the water from the outside of the glass, will we still have the same problem? Well, let's find out. Hydrophobic coated glass, non-hydrophobic coated glass, or just regular glass.
Water likes to stick to surfaces, but it can't stick to one coated in hydrophobic coating.
That's impressive. Should we try something else?
Well, that's one way to solve the dribbling glass problem. Except you can't coat your glasses at home with hydrophobic coating because it's not good to eat.
The secret is using a container that has a very sharp angle between where you're pouring the water and the underside of the glass, like this jug. And there you go. Now I can enjoy a nice glass of water with my cheese and crackers. Oh, right. Wait, hold on. I will remake the crackers into, see, look, see, it's fine. It's fine. I'm not really gonna eat that. I'm just kidding.
Chris and I are maxing out our hydraulic crusher.
Yes. Before we get to that, I have a little game I want to play.
Okay, great.
Okay. You can pick either the small one.
The big one.
Okay.
So what's the game?
Simple thumb war. I'm gonna press down this side. You press down that side. We'll see who wins.
Okay, ready?
Yeah.
1, 2, 3, go. Oh, wow, that was really tough. Why was that so hard?
Well, Phil, I'm just really strong.
Wait a minute. My turn. Okay, 1, 2, 3, go. Yeah! See, pushing down on this one is way easier. You wouldn't think that the small syringe would be easier. Why is that?
The reason for it is that you have to push this one down a lot farther than you have to push this one down.
let's see.
See how far this one goes, and this one's barely
This one
moving?
travels much more. This is how we can exchange a little bit of force over a long distance.
That's right.
To a little bit of distance at a lot of force.
That's exactly right.
Just like the lever, it's a mechanical advantage. But in this case, it's hydraulic advantage.
That's right.
Chris and I push down on small syringes, which gives us more force on our larger syringes. Our crusher was ready to go.
Ooh, how about an orange? 1, 2, 3.
We squeeze down and... Then we tried a walnut.
Are you allergic to nuts?
I am not.
1, 2, 3.
When we tried a golf ball, we reached the limit of what our plastic syringes and our hands could do.
We need to come up with a stronger, more awesome crushing machine using hydraulics.
That's right. I have some ideas.
Okay, good. We can use metal.
We can use metal.
And we
we can go bigger as well.
Ew, this water is gross, but I'm gonna drink this water. Why? Well, because of science. No, but I'm not gonna drink the water like this. First, I'm gonna use the power of science to help me clean it. How? By using gravel. Gravel, yes, gravel. So, say I've got some dirty water, and there are particles floating in that water. Large particles, your rocks, your wood. These styrofoam bits will act as the large particles. You pour it into the gravel, and the large particles get filtered out. See? Nothing but clean, clean water. Yeah, I know what you're thinking, Phil. That's not really clean yet. That's because we haven't done step 2. Sand. Sand? Yes, sand. Let's say that these plastic beads are small particles. That filters out the tinier stuff. There, huh? Clean, right? No, it's not very clean. So we filter the water in the next step with charcoal. What? Charcoal? Yes, charcoal.
Charcoal works just like gravel and sand, except on a microscopic scale. Say these bits are tiny particles you can't even see. The charcoal catches these like the sand and gravel caught the larger particles. This is called a
Gravel, sand, and charcoal filter.
The gravel catches the big particles, the sand the smaller ones, and the charcoal the microscopic ones. These kinds of filters are used all over the world to clean drinking water.
Delicious. Science.
Max Historica.
This is Archimedes.
What? Who said that?
It's me, the narrator. We're doing a segment.
Oh, well, I was working. Don't sneak up on a guy like that.
This is Archimedes, an ancient inventor and one of the greatest scientific minds ever. One of his famous inventions was the Archimedes screw, which was used to make holes in wood.
No, that's not what it's for. It's for water.
Right, used to make holes in water.
What? No! Look, did you even do your homework?
Hold on, it's here somewhere.
Look, I'll just show you. You see, in ancient times, we had many uses for something that could lift water up. From a well, or to take lake water from the lake and put it into a farmer's field, and that sort of thing.
Okay, I've got it from here. So, Archimedes invented a screw, and he drilled a hole in the side of that container.
No. Look, just sit down. I'll explain it, okay?
I am sitting. I'm in a voiceover booth.
Good for you. Now be quiet. Now look. What you do is you put the screw in the water like this, and then you want to raise the water higher, you see? And so turn it around like so, and the water fills each gap in the screw, and it starts to come up. It gets to the top, and look at this. Look, we've got water coming at the top there. The water is being pumped up. It is the first water pump.
I see. Still seems like a lot of work to fill a glass, but it's very cute.
No, we made them bigger. We obviously were not going to make them this big. This is not very useful.
Right. Archimedes, one of the greatest scientific minds ever. Chris and I are maxing out a hydraulic crushing machine. We tried one out of plastic, but now it's time to make one out of metal. These are called hydraulic cylinders, and they work the same as our syringes. Small ones on this side with a lot of travel, and then a larger one on this side to multiply the force. And some mechanical advantage with a lever to help us push even harder. We tried crushing a watermelon, and it worked great.
So what else do you want to crush?
We crushed a coconut.
It's cracking. Oh, there we go. Oh, it's gonna leak.
And then a can of pop.
Science Max Cola, now in the new, smaller can.
Let's really challenge this press. Perfect.
A piece of wood.
We tried to crush the wood, but we weren't able to get it to budge. So it's time to max it out even more.
I think we're gonna need like a multi-story, industrial-sized hydraulic press.
You know where we can get one of those?
I do.
Awesome. This is water. Things float on water, like pool noodles and wood and toy boats. And now we're gonna do an experiment with how paint floats on water. How's this supposed to work again? Oh! I'm supposed to take the paint out of the can first. This is a fun experiment you can do at home. All you need is a container, some water, and paint. But not just any paint, special paint you use for hydro dipping. That's hydro, meaning water, and dipping, meaning dipping.
Carefully pour the paint on the water and add a few different colors. Then take a stick to swirl it up into a pattern.
Then you get something you want to paint, and you carefully put it in like so. But don't pull it out as soon as you get it in. You have to spread the paint away because it'll stick when you bring it back out. And then when you pull it out, whoa! Hydro dip. Let that dry, and then you have a very cool painted toy. Let's do some other stuff. This is a bike helmet.
If you put tape on what you're painting, you can remove it later to make parts that aren't painted.
Skateboard. Whoa! Oh, that's pretty cool. Now to max it out. Hydro dip pants.
Wearing the pants when you do this is super messy and not something you should try at home. But the results weren't bad.
Science pants! Science pants! Science pants. One of the ways you can experience the power of water is watching it wash away dirt. You can experiment with this yourself by making your own erosion table.
To make your own, fill a plastic tub with sand and tilt it up. Cut a hole in the tub at the low end and put a hose with a trickle of water at the high end. Then to complete your model, fill it with
A little happy town.
This small model shows how rivers cut their course to the ocean by following the lowest point. Try to design your town and the layout of the ground so the river goes around the buildings.
I'll see you later. I'm gonna take a swim in the river now.
There are lots of ways to experiment. Change the amount of water, or the steepness of the angle,
Look at the soil, it's all getting eroded over here.
or the way the town is laid out.
Every time you do it, the river goes in a different direction,
And have fun.
Oh, phew, I'm tired. I'm just gonna lie down.
and that is the power of water.
Chris and I are maxing out a hydraulic crushing machine.
What about this? Is this what we're gonna use?
We went to the Natural Resource Canada's CanMet Materials Laboratory, which is a federal research lab.
Oh, this is good. Oh, look at that! Oh, is this what we're using?
No, Phil,
Oh,
it's
I can
actually-
use this. Hold on, let me figure this out.
Maybe later.
Really?
It's just over here.
CMAT is the largest research center in Canada dedicated to metals and materials research.
This is it.
Oh,
This is it.
yeah, right! Hydraulic press. How much force does this apply?
This can do 2 million pounds,
That's over 900,000 kilograms.
which is about 20 cars.
Let's crush some stuff! Oh, crushing! We gotta get the stuff. Okay.
We started out with the piece of wood which defeated our last press.
And go!
That sound.
Awesome. Reversing.
It turned our wood into a pancake.
Whoa, totally flathead.
So it was time to try some other stuff. We crushed a ball of plasticine.
That is neat. You sort of made a rainbow.
Yeah.
Aluminum foil.
Aluminum foil.
Yes, it is now a solid plate of aluminum.
And a basketball.
Basketball. Good thing we got these earplugs in because when it pops, it'll be loud.
What?
Never mind.
This hydraulic press was so maxed out, we had to think of the toughest stuff to crush. We crushed hockey pucks, a safe, we crushed a hydraulic jack with the hydraulic press.
This is a metal vise. Hard, strong,
Yeah, steel.
heavy, steel.
Whoa, look at it bend. Wow.
Now it's time to crush a bowling ball.
It totally exploded. Science Max! Experiments at large, hydraulics. Whoa. Nicely done.
So fun.
I should reverse it and we should start cleaning all that stuff up,
Yeah,
huh?
I think so.
Okay, reverse.
34. Take 36.
I don't know why I thought that would work.
Take 52.
I'm feeling today we're talking about friction. Sorry. Okay. Whoa. Friction. We did it. We got it, everybody. How many takes was that? Oh. Well, still, we got it. Good work. As you may have already guessed, today is about friction, and here's a really easy friction experiment you can do at home. All you need is a piece of wood. You don't need the frame, and you don't have to do anything fancy to it. Just put one end up on a couch or a coffee table and make a nice ramp. Then you want something to slide down that ramp, and I like to use a piece of wood. Now check it out. Wood ramp, wood block. The friction is so much that the wood slides to there. Now what I like to do is take a little flag and mark the results. Recording the results is good science. Now here's where it gets fun. Get another surface and attach it to the wood, like carpet and wood. Let's see how far this goes. Not as good. All right, record the results. Cardboard. Ooh, nicely done, cardboard. Foam. And this wood has been waxed, like on a floor wax, which makes it nice and slippery. Let's see how that does. Ooh. And now the ultimate ice attached to wood. This is actually harder to do than I thought. All right, let's try it out. Ice! The clear winner. Not a big surprise right there. And get this, once you've done all of that, you can change the surface of the ramp. You can go to waxed wood, carpet, foam, cardboard. Well, well, yeah, you get the idea. Record all the results, compare them, and there you go. Friction ramp experiment. And that's what we're gonna be maxing out today. So come on, let's go. Check it out, I've improved the portal interface. Watch this. Yeah, and then I can scroll through experts, and oh, this is gonna be fun. And I've got my coordinates right there. Whoa. That's never happened. Okay. Hey, Sarah!
Hey, good to see you again.
Good to see you too, Sarah. From Mad Science, you're gonna help me max out friction!
Yeah, friction.
What do you think of my maxed out friction room?
It's amazing. It's so wonderful. So how are we gonna max out friction today?
In the lab, I had a ramp, and I had stuff with different surfaces on it.
Oh, that's so cool. It's too bad you don't have it here. We could totally test that out.
I can bring it here.
Awesome.
I have a new app on my phone that talks to the portal, and let's see. That's not what I. Oh, hold on. Okay, there we go. And whoa. Well, I can do this. I just it needs an update.
Yeah.
That's what the.
There we
it
go.
is. Okay.
Perfect.
So here we go.
Amazing.
The friction ramp, it's pretty simple. You just take, I've got blocks of wood with different surfaces.
Amazing.
And then you just slide them down the ramp.
Right. So cool.
Yeah, so what if, to max it out, what if this is us?
We're a block of wood?
No, I mean like we are on the block of wood and then we can try changing the bottom. I guess a block of wood isn't the right thing to use though.
Right, yeah. Maybe we could use like a sled.
Oh, yeah, okay, like a snow sled. That's a great idea. Okay, so we'll tell you what. I will portal in a sled for us.
Are you sure you want to portal it in?
I'm sure. Just stand back
Okay.
though. Okay. Ha!
Ah, there we go.
Maxed out friction slide! You ready, Sarah?
Yeah, I'm ready.
Okay, here we go.
All right.
Sarah and I pushed each other around on the sled, which was fun, but it was also tiring.
It's pretty hard. This is my turn.
My turn.
All right.
Yeah! Whoa, friction! Yeah, friction! Yeah! Yeah, friction!
But we soon realized it'd be pretty hard to measure how much friction there was.
You know how hard you were pushing?
I had no idea how hard I was pushing.
A lot, but that doesn't really help in science terms. So
Exactly.
what do we do?
Well, with your first experiment, you used a ramp. Could we maybe put a ramp up in here?
In here?
In here, yeah.
I guess.
Then we can measure also how far we go so we know how much friction is being used.
Right, so we have our control, and then we have all the, just like the blocks.
Exactly, just like the block.
Okay, great. So we'll get the ramp, we'll get a bunch of wood,
Yes.
we'll get some tools.
Yeah.
The case of the missing friction!
It was rough all over in the big city. My toughest case yet, and I felt like I was getting nowhere. Someone stole all the city's friction. And it was my job to find out who and get it back. But after a week, I was no closer to solving the case. It was hard to get anything done now that there was no friction. Uptown to downtown, people were sliding all over with no way to stop themselves. It was chaos. Chaos, I tell you. But if there was any detective that could solve the case, it was me. But it's like my grandma always said, it's tough to follow leads if you can't sit in your chair. Nothing stays put in a city without friction. And you never appreciate something till it's gone. The phone rang. Sure, I wanted to answer it, but it slipped through my grasp just like this case. The mayor was on the line. He wanted to know if I'd made any progress. But I felt I was going in circles.
I'm gonna have to call you back, Mr. Mayor.
Without friction, you couldn't do very much at all. It was going to be my toughest case yet. Sounds good. Sarah and I are maxing out a friction ramp. Step 1, make a giant ramp.
There, are we done?
Hey, I think so.
We're done. But it proved a bit hard to lift up to the second floor. Fortunately, Sarah had an idea.
Maybe we could use this crane.
We use the crane!
Oh, yeah, I've got a 5-ton crane at Science Max headquarters. Good thinking, Sarah.
So we rigged it up and tried it out. The bonus was we could make the ramp any angle we wanted.
Okay, time to get my helmet, because don't go any higher than that, because I don't have my helmet. And then we will start sliding down.
All
Friction
right,
ramp!
friction.
I got on the slide and Sarah lifted it up until I started moving.
Ah!
And that allowed us to record our results.
We're at 2 meters.
2 meters! Recorded. First recording done, now we switch it up.
We tried it again with Sarah on the slide to see if she slid at the same height. And she did.
Yeah.
Now we have a way to record the results. The plastic sled went down the ramp at this height. Things with more friction will mean the mark is higher, and less friction will mean the mark is lower. So then, we tried it with
Cardboard! Cardboard! What did we get?
and it was?
A little over 2 meters.
Meaning?
Cardboard is a little bit less slippy than the plastic of the sled.
All right.
Ready for carpet sled?
Good to go.
Here we go. Oh, past 2 meters. Oh, almost 3.
Here we go.
Carpet had even more.
Oh my gosh, we're going to the side.
Whoa!
That was so cool.
That was exactly 3.
Then we tried foam.
Coming up on 2 meters. All right, coming up to 3. It won't go up any higher.
And just like the wood block, the foam didn't slide at all.
What if I do this and then I slide? Right, so, friction sled on foam, highest friction of all of the materials.
Oh, hello there. Here's a fun science experiment you can do with science and friction together. Take 2 books, put them on top of each other, and pull them apart. Ooh, not too much friction. But if you take the books and you interleave some of the pages, maybe 3 or 4 parts, and try it again, pull them apart, they're a little harder to pull apart. That's because the friction for more pages touching each other actually starts to add up. So, what if we were to take 2 books with a lot of pages and very carefully and meticulously take each page individually, one at a time, and overlay each one and go back and forth? These are 2 books completely shuffled together. The elastic band is actually just to hold the covers together. All right. So, now the friction between all of these pages, when I try to pull it apart, makes it pretty much impossible. Now, there's 2 things going on here. First of all, when you start to pull the books apart, the pages start to stick together because they squeeze together, because you're pulling and they're squeezing. And the fact that there's so many pages sticking together, the friction builds up to a degree that is actually very impressive. But don't take my word for it, let's max it out. Here is another 2 books, elastic just to hold the covers. This one clamped to the wall, and I'm gonna pull on this one. Science! Still don't believe me? Well, let's max it out some more. 2 books, all the pages layered together, held together only by friction suspended over a giant vat of slime. Now, let's see how much faith I have in science. Friction! Yeah! Okay. Okay, oh no. Okay, now to get down. Okay, hold on. And then... Science! That was close.
Sarah and I have used our maxed out friction ramp and compared the regular sled to cardboard and foam. What's next?
We've waxed the bottom of this sled, and we're gonna try a wax sled next.
Wax sled!
All right, here we go. Right.
1 meter.
Oh boy.
1.5 meters.
Whoa!
Wax sled! Woo! The slipperiest yet, only 1.5 meters.
That's awesome. Do we have anything that's more slippery?
Yeah, we do. We have ice sled. Are you ready to try it out?
So ready to try it out.
Okay, let's do it.
All right.
And
There we go. Whoa! That was awesome.
look how far you went.
That was so cool.
And only 1.25 meters.
Least amount of friction.
Ice wins. So, I think we should do something else to max this out, though.
Maybe bringing it up a little bit more and
Yeah.
using something with less friction.
Wait, I have an idea. Yeah, okay, come with me. This is a climbing frog. Why does he climb? Because of science. I pull on this rope, and then I pull on that rope, and I pull on that rope, and he climbs up the ropes. And why? Well, because of friction. The secret is 2 straws.
The straws are pointed away from each other at the bottom. This allows it to climb thanks to friction. Take a closer look. When I pull on one string, it pulls straight, which makes the frog pivot. That string slips through the straw because there's not a lot of friction, but there's lots of friction on the other side because of the angle. So one side of the string goes down, which makes the other go up, which means the frog goes up with it, all thanks to friction.
So now, let's max it out. This is a super maxed out climbing frog.
Just like the small version, I have a rope going through 2 tubes. I pull on one rope and the other holds on by friction. Then I switch.
And it does work. It's just a lot harder to pull on the ropes. But it totally works. Whoa, careful. Whoa. There, and then this one, and then that one, and then that one. Yeah!
giant climbing frog! All because of friction. Here's another way to defy gravity using friction. Get a plastic water bottle and fill it with rice.
Take two.
So get a plastic water bottle and fill it with rice using a funnel. Then take a shish kebab skewer and stick it into the bottle and nothing happens. But if you tap the bottle down, the rice starts to pack in a little bit better. See how the level of rice is lower? Which means you can add more rice. Pack it down even more. And you can even use something the same diameter as the mouth of the bottle, like, say, a highlighter. And make sure all the rice is as packed in as you can get it. There. Now the rice is really packed in there. And when I stick the shish kebab skewer in, the friction between the pieces of rice and this wood is enough to lift the bottle using nothing but friction. Now, let's max it out. I filled this 20-liter water cooler jug full of rice, and it's really heavy. I wanted to see if I could lift it using nothing but friction and this dowel, which is just a round piece of wood. All right, here we go. Ah, science! I'd max it out even more, but I don't think I could lift anymore. It's okay, I can just fit.
Newton's first law in 60 seconds.
Newton's first law says an object in motion tends to stay in motion. So why don't they? See, if I was to throw this, it doesn't stay in motion, it doesn't keep going, it slows down and falls to the ground. Well, the whole law states an object in motion tends to stay in motion until an external force acts upon it. So what forces are acting upon this? Well, gravity for one, pulling it down towards the ground, and friction, specifically air friction, slowing this down and making it stop. Now, if you were to have something very light with a lot of surface area, it would really be affected by air friction. You wouldn't be able to throw it very far at all, no matter how hard you tried. So there you go. Newton's first law, an object in motion tends to stay in motion unless it's affected by an external force, such as friction, like air friction. So there you go.
Sarah and I have recorded a lot of results on our ramp by raising it till we started to slide.
Here we go.
Now we've decided to raise the ramp to the highest point and see how far we can go using some low friction things, like a wheeled cart.
I've made a double bike cart.
Wheels are great for moving. They have rolling friction,
Ready?
which is different from sliding friction.
What happened?
You went through all those boxes back there.
That was it. We went really far. Total fun. Let's try something else.
So what are we gonna do next?
Now we're gonna do the frictionless thing that we have at Science Max headquarters, a hover disc.
Oh my gosh, that's so cool. Where did you get it?
Built it, season 1.
Amazing.
As you may remember from that episode, a hover disc uses air to greatly reduce the friction with the ground.
Here we go.
So what would a hover disc do on a ramp?
Right.
Only one way to find out. Let's recap. Friction is when two surfaces rub against each other. You can have a very small amount of friction or a very large amount, depending on the materials. And using science to reduce friction results in the best sledding experiences.
Nicely done. Science Max, experiments at large. Your turn?
My turn? Yeah, let's do
Okay,
it.
so take those, and I'll get this, and then I'll give you the helmet. And then we gotta rebuilding the boxes is like the hardest part of this
Yeah.
whole situation. Hey, Science Maximites. Today, we're doing the egg drop experiment, and oh no.
Oh no! Ha 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 ha. Things like this egg carton are designed to cushion the eggs in case it accidentally gets dropped, or in case you want to stack something on top of it. The egg drop experiment is a great way to design some really cool stuff, and it's easy to understand. You take an egg and you drop it. So, let's get designing our egg drop experiment. First, you're gonna need an egg. No! Why? Everything's fine. 1, 2. Right, so where were we? Yes, you need an egg. And you need an adult's permission just in case you make a mess. Now, there are 2 ways to approach the egg drop strategy. You can cushion the blow, or you can slow the descent. And there's tons of ways to do either of those things. Cushioning the blow, pretty easy. You get a whole bunch of soft stuff that the egg can fall into so it doesn't break when it hits the ground. Or slowing the descent, you do something like this parachute idea, and it slows the egg as it falls so it doesn't hit the ground with as much force. And you see, the egg is totally fine because it went slowly to the ground. Now, this episode isn't just about dropping eggs. It is about material science. The kind of materials that you use make a big difference. Styrofoam, tissue paper, very light plastic, very light string. If we were to say use different materials for our parachute version, say wood instead of styrofoam and heavy string and very heavy fabric, I wonder if this would work as well. No, it doesn't. So there you go, Science Maximites. Materials make a difference. And that's what this episode is all about. Material science. Cutting edge materials, new materials, and dropping a whole lot of things to see if they break. But first, I need an expert to help me. Let's see. Who should I pick? Jenna from the Ontario Science Centre would be great at this. Okay. Come on. Huh? Hey, Jenna!
Phil, how you doing?
Jenna from the Ontario Science Centre is gonna help me max out the egg drop.
Yes, but we're gonna need an egg, right?
Yeah, no, I had one when I came through the door. Whoa!
Woo! So do we have some more eggs?
No, that was the last one. But that's okay, because I think we should max out the egg drop, so we need something larger than an egg.
How about pumpkins?
Pumpkins, great idea.
And now we need somewhere to drop them from.
Oh, I already know that. We should drop it from up there.
I think we're gonna need a control group, a control pumpkin, if you
A
will.
control group. You need that in science.
Right, if we're dropping pumpkins and we have nothing to compare it to, then we can't make appropriate observations.
Right, so we just drop a pumpkin straight to see what happens.
Yeah.
Awesome, so we'll get a whole bunch of pumpkins,
Yes.
and we'll start building.
Yeah, let's do it.
And then we'll also probably need to clean this up. Wait, I got a mop over here.
This is our control pumpkin. A control in science means a version you don't experiment on, so you can compare the results of your experiment. So this is what a pumpkin does when dropped with nothing to cushion the fall. Jenna and I really have our work cut out for us because a pumpkin has a lot more mass than an egg, which means it's going to be much harder to stop once it's moving.
So now all we have to do is come up with a couple ideas to stop that from happening.
All right, let's do it.
Science. Yeah. You want the best material around? Well, you come to the right place. I've got them all. I got you flubberoid, magnoplex, flexoweed, pastotherm, blooperfoam. You need hydrogelatinous substrate? I got it. But you know, all those fancy materials are nothing compared to the good old-fashioned spiderweb. Huh? Hey, where's Gary? Ramona, Gary got away again. You know, people ask me, Sal, is it true spiderwebs are stronger than steel? And I tell them, it depends. When you look at a rope or a thread or a fiber, you talk about its tensile strength or its ability to withstand force before breaking. But you're comparing different things, so you have to compare them by thickness. So if you're comparing a steel cable to a spider web of the same thickness, then yes, steel is stronger. But spider web is 6 times lighter than steel. So if you are measuring strength to weight, spider web wins every time. Gary! So why don't we build more
things with Spiderweb? Well, for one thing, it's sticky and difficult to work with. Almost finished knitting this Spiderweb sweater. It's only gonna take me about 80 more hours.
And it's not easy to train spiders.
Okay, Steven, one long, non-sticky thread and you get a cookie, okay? And, hey, where's Marco?
And Petunia. Huh? But no need to train spiders now because modern science has surpassed the spider web. Enter carbon nanotubes. Huh? This thread doesn't look like much, but it is made of tiny little tubes made of carbon atoms.
Think of them like a straw.
But a really long straw.
Carbon nanotubes are incredibly light and strong. Remember when we compared strength to weight? Well, steel is heavy. Spiderweb is about 6 times stronger by weight, and carbon nanotube is about 50 times stronger than that.
That's so great.
So why aren't we making everything out of carbon nanotubes?
I'm gonna knit a carbon nanotube sweater.
Well, first we have to make them cheaply enough to be affordable. There you go. One carbon nanotube sweater. $480,000.
But material scientists all over the world are hard at work trying to find ways to make carbon nanotubes faster and cheaper. And soon, they'll be everywhere. And then spiders can go back to spinning their webs in peace.
There you are, Gary. Where's everybody else? With Petunia and Marco and... What do you mean they're in my jacket?
Jenna and I are coming up with solutions to the pumpkin drop. We have 3 material science strategies. Strategy 1, polymers. Something is a polymer if it's made of long chains of molecules. Everything in this category is a polymer-based solution. Rubber and elastics are polymers, so I thought, what about a trampoline?
Look to the left a little bit.
My left or your left?
My left. Alrighty, here we go.
And it works great! The pumpkin totally survives until it lands from the bounce.
That's it, like it's a success and a failure.
Balls are made of polymers like rubber or plastic, so how about a bag of balls?
There's the pumpkin. Whoa! I think that worked. Whoa, mostly unscathed.
Almost there. Almost there.
Right.
Bungee cords are made from elastics, which are a polymer, and it worked, I think. I mean, it stopped it from falling, but never made it to the ground, unless we unhooked it.
Technically, it survived better than any other pumpkin, really. Here's another polymer solution. This is cornstarch mud. It's a liquid, but if you hit it, if you impact it, it turns rigid.
Right, so that could protect the pumpkin.
Oh, yeah. And now,
The rest.
we add more cornstarch. Cornstarch mud strategy.
But it turns out hardening on impact doesn't cushion the pumpkin much.
Yeah, a bit of a problem there.
I don't think this worked.
And every scientist's favorite polymer,
Giant tub of slime!
Where did you get a giant tub of slime?
Episode 6.
All right, let's check it out. Little slimy, all awesome.
Now let's recap. This is our control pumpkin, so solutions work if they do better than that. Trampoline? Yes. Then no. Bag of balls? Yes. Bungee cord? I think we need to disqualify that one. Cornstarch mud? Barely. Slime? Yes. Not bad for our first round.
Science!
Advanced materials in 60 seconds.
Scientists and engineers are always coming up with new and advanced materials. Some are for spaceships, and some are just for fun. I'll show you a few. Hold on.
Like, oh, this. This is a thermochromic mug.
It's cool right now, but if you add hot water, it changes color.
Ooh, this spring is made out of nitinol wire. It's also called memory wire, and I'll show you why. The reason it's called that is because it's a metal that remembers its shape. This one remembers being straight. All I have to do is drop it in hot water and it turns back into a straight wire. How cool is that? Science! Oh, this is Ulexite. It's sort of a see-through rock, but it's made of perfectly aligned crystals. So it's not just see-through, but the image actually gets transmitted from one side of the rock to the other. Advanced materials are really cool. I can't wait to see what science comes up with next.
Now it is time to talk about an amazing natural polymer. It is hagfish slime? Ugh. Still, well, hagfish, that's probably just an unfortunate name for the fish. I'm sure the fish itself doesn't. Ugh. Okay, so hagfish makes slime, apparently. When a hagfish is attacked by something that wants to eat it, like a shark or an eel, it secretes a tiny bit of a natural polymer. That's this little white bit right here at the end of this test tube. Now, it doesn't look like much right now, but it reacts with seawater. Watch this. Hagfish slime is very interesting to scientists because you start with just a tiny little bit and add seawater, and suddenly you have a lot of slime. Whoa. This stuff is actually pretty cool. Hagfish slime is a natural polymer. It's made just the same as the other polymers out of long chains of molecules, but it's naturally produced by a living organism. And because it's naturally produced, that means it's biodegradable. Hagfish slime. It's pretty cool after all. Ugh.
We've had some good successes with polymers.
Whoa, mostly unscathed.
Almost there, almost there.
Right.
Now it's time to try our foam solution. The first foam we use is fruit netting.
Foam fist bump. Boom. See? That didn't feel like
Didn't
much at
hurt
all.
Which didn't seem like enough protection.
Pumpkin ball. Pumpkin, actually, pumpkin sphere.
Wrapping the pumpkin in a sphere of foam.
Go pumpkin sphere!
It worked better, but not perfectly.
Uh-oh. It split right down the middle.
Pumpkin cube!
Phil?
Yeah.
Phil, what is it?
Wrapping the pumpkin in a cube of foam. Better than our control, but you can see the pumpkin crush as it lands.
Oh, no. Phil?
Totally great! How much did it hold together?
Not at all.
I'll give it 3 cubes out of 7.
We need more protection,
Pumpkin helmet.
which leads us to a bike helmet solution, which worked the best of all so far.
Totally survived!
Oh, my goodness!
Yes, I know, this pumpkin's a bit smaller than our control pumpkin, but our big pumpkins wouldn't fit inside helmets, and we figured it was only a fair test if we used a pumpkin the size of your head.
This is why you wear a helmet, Science Maximites. Look at that. Unharmed.
Expanding foam sealant.
And we spray it all the way around the pumpkin.
Expanding foam sealant is special stuff used to insulate gaps and cracks in the walls of your house. It comes out of a can soft, but then expands and hardens to foam.
A full pumpkin completely covered in expanding foam!
Turns out this stuff is made for insulation, not absorbing shock.
Our beautiful foam pumpkin.
I don't think it worked that well.
So now we recap our foam solution. Fruit netting. No. Foam sphere? Yes. Foam cube? No. Bike helmets? A big yes. The only perfect pumpkin yet. Expanding foam? No.
So that's it for our foam solution.
I think we should move on to armor now.
Yeah, all right. Foam. Foam. Foam! How can they all be foam? Well, foam usually means something to do with bubbles. There's all kinds of solid foams out there, and they can be squishy or not squishy. And they're usually light. Air is an insulator. That means it does not conduct heat or cold very well. You see, I cannot tell this ice is cold until I get my finger really close to it. Yeah, there it is. There, I feel it. And because foam is full of air bubbles, it makes a great insulator. That's why we make coolers out of foam. So what's the best, most advanced foam out there? It's this. It's called Aerogel, and it's 98.2% air. It is super light because it's mostly air, and it's a great insulator because it's mostly air. It's great to pack things in as well, and NASA uses it on the Mars rover and in spacesuits because it's such a good insulator. Cool. Or not cool because, you know, it's an insulator, so it would protect from the cool.
We've tried polymers.
Little slimy, all awesome.
We've tried foam.
Uh-oh. It's split right down the middle.
Now it's time to try armor. Anything that protects the pumpkin in a shell of some sort.
This does not look like armor, Jenna. This looks like pumpkin soup.
Our first solution may not seem like armor, but it's a hard shell and the pumpkin floats in the water. When we drop it, the bin explodes, which slows the pumpkin down a lot. The result? Not perfect, but still, remember, it's better than our control.
So compared to the control pumpkin, that did pretty well.
That was pretty good.
Yeah.
I'll give you that.
What is this?
All right, well, we've got a pumpkin covered in knee pads.
Knee pad pumpkin!
Knee pads are armor for your body. So wrapping the pumpkin in knee pads...
Knee pad pumpkin!
Drop it, Bill!
Didn't seem to make much of a difference.
Maybe it didn't land on a knee pad. Maybe we just missed. It ended up in between the knee
I
pads.
think that must be it. It's looking a little rough.
But using sports equipment gave me an idea for using an advanced material. It's called sorbethane, and it's used in modern sports equipment. It disperses impact.
See, watch this. Okay, so I've got a hammer, and I hit the pumpkin here, and it goes right into the pumpkin, right? So, take that. Now I hit it again on the sorbethane, and haha, see? Nothing. So I thought maybe this will cushion the impact.
The result? Not bad.
I don't think it dispersed it quite well enough. There is a crack coming right from the hole that you made with that hammer.
Okay, so the hole might have structurally weakened the pumpkin a little bit. So the sorbethane did a pretty good job, actually.
Yeah.
Good thing it is in athletic equipment. That's what it's for.
Carbon fiber is a very modern kind of material.
It's carbon meshed together and then glued down, so it's super strong.
Super strong, and the pumpkin is contained inside. It's like double shields.
Yeah, so can I test how strong this is?
Oh yeah, this is the armor solution, so let's try it out.
See, we better try it.
Whoa!
But when we drop it, we realized there were too many hard surfaces. And not enough cushioning. But the carbon fiber held up really well. Slowing the pumpkin down and cushioning it is the answer, which leads me to my final solution.
I call it the lunar lander. That's what I was doing. I was coming in, right?
Right.
Yeah.
See, I thought we were supposed to be doing armor?
Yes. So this is armor. I know it looks like foam, but you see armor like in a helmet, it's supposed to crumple to protect your head, right? So
Right.
this will also crumple because it's not just foam, there's wood inside. So the wood is supposed to break and then the foam bends and the whole thing is supposed to cushion the impact of the pumpkin. Ooh.
That looks pretty good.
The landing crushed and broke a lot of the arms of the lander, but the braking cushions the impact.
Oh, what do you think?
I think it's good. I think we're good.
Look at that.
And now the awesome recap. Remember, the difference between doing science and just having fun is recording the results. Water bin? Yes. Knee pads? No. Sorbethane? Yes. Carbon fiber? No. Lunar lander? Yes. So, we've had some successes and a lot of failures, and we've learned a lot of things about different materials. And we have one pumpkin left.
There you go, Science Max Experiments at Large, pumpkin drop. Thank you, Jenna.
Thank you, Phil. That was awesome.
And we still have one pumpkin left. Whoa, whoa, no! I got it. I got it. It's fine. Everything's fine.
Fine.
We can
I got this.
Yeah, we
Fine.
can take that up.
Yeah, no, it's
You got it. You got
good.
it. Careful. Oh well.
Oh, okay, well.
Make that 0 pumpkins left.
Greetings, Science Maximites! My name is Phil and welcome to Science Max Experiments at Large. Today we're gonna be looking at air pressure and friction and simple machines like levers, pulleys, and gears. We're gonna look at some rotational energy, some spring tension, and gravity. We need all those things because we're building Rube Goldberg machines! Rube Goldberg machines! Rube Goldberg machines! Rube Goldberg machines! Rube Goldberg. You heard me say Rube Goldberg machine? Okay, we got that part? Okay, good. Rube Goldberg was a cartoonist who came up with the idea of having a simple task done by a machine that was extremely complicated. There are Rube Goldberg competitions all over the world, and there's only a few rules. First, a human can only touch it once by starting the whole thing off, and then the machine has to work all on its own. I know what you're thinking. You're thinking, Phil, what's the science behind a Rube Goldberg machine? Well, it's all about changing energy. Remember, you start the whole thing off with just a little push. But if you want the machine to keep going and going and going, you have to come up with clever ways to add more energy to the system so you've got more energy to keep the machine going. So check this out. A bunch of stacked dominoes, which will start a chain reaction that leads to this mouse trap, which has all of its energy stored in the spring tension, which will release the ball. Boing! Check this one out. It's a bunch of pulleys, and there's a rope that goes up and down and up, attached to this lever where there's a ball, and there's a big heavy weight here. And when the weight gets knocked off the table, the ball falls into the hole and then goes down the tube, and so on. Check this one out. Here's a great way to change the direction of something. Say the ball falls on this lever. Well, it's weighted on this end, but then the weight falls off, and the ball goes this way. And, the portal turned on. I gotta pick an expert. Okay. Hold on a second. 10 seconds before the portal resets. Sonia from the Ontario Science Center. Perfect. And there we go. Tons of time. 3, 2, 1. Sonia!
Hey.
I portaled in 3 blocks away. I had to run here.
Okay. You're here now?
Yeah, I didn't put the coordinates in when I left. Anyway.
It's okay. Breathe.
Sonia from the Ontario Science Center. I'm glad you're here because we are gonna build a Rube Goldberg machine.
Really?
Yeah.
Oh my gosh, I'm so excited.
Yeah?
Yes.
I'm excited too. Check it out. This giant room. I've never done anything with it, so why don't we build a giant machine in here?
Why not?
Okay, so here's the rules. The Rube Goldberg machine has to start with one simple thing, right?
Yep.
So we're gonna start with this marble, and we send it on its way, and then a whole bunch of stuff happens, and at the end, we press that button.
That button?
Yeah.
What does it do?
I've never used it before, but when we hit that button, we get cake.
Cake?
A cake will portal in and we'll have cake.
Oh my goodness, can we get chocolate cake?
We can totally have chocolate cake.
All right, now I'm really, really excited.
Okay, so can I start?
Absolutely.
Great, because I saw some stuff over here.
Okay.
This is a pendulum. It's a weight that swings. It swings back and forth. Pendulums are pretty simple. It swings back and forth. Predicting the path of a pendulum, pretty simple. It's gonna swing back and forth. But wait, as I make it so much more complex by adding a pendulum. Now I've got a pendulum down here, and that one swings back and forth, and I've got a pendulum up here that swings back and forth. What will happen to this part of the pendulum when I let it go? Can you predict? Let's find out.
This is a double pendulum, and predicting the path of a double pendulum is really difficult. It's still simple physics, but because there's a moving part attached to a moving part, it makes it way more complex.
So, the question is, can we max it out even more? Of course we can. These are chaos pendulums. This one's a lever, and it's got another lever on the end. Whoa, and this one here is a perfectly balanced lever, and it's got a pendulum on either side. Whoa. Whoa. Scientists and engineers have always said that the more moving parts something has, the more complex they are. Science.
Sonia and I are taking turns building our Rube Goldberg machine. The first section was my turn, and I explained it to Sonia.
Right here, we have what is known as a ramp. Ooh, yeah, I know you know.
Fancy.
That. Right, so we put a marble on the ramp that rolls along this thing into what is known as a pylon. And then we've got these guys right here, which are dominoes. And when that falls off the table, it'll pull on the string, and then it's attached to this. Now, this is the release mechanism, so when that string gets pulled, it will let go, and it will fire this, which is a trebuchet.
All right, should we test it out?
Absolutely. You
Can
want
I
to try
try
it?
it?
Yeah, please.
Yeah.
Okay.
Okay, 3, 2, 1. Huh.
Wait.
Didn't go. Why didn't?
Well, the domino doesn't seem to be heavy enough to make this contraption fire.
You know what, Phil?
What?
I have an idea.
Oh, yeah?
Maxed out dominoes.
Maxed out dominoes. I love that idea. Why are they maxed out? Do they glow in the dark?
We'll see.
Do they produce electricity?
We'll see.
Do they talk to animals?
We will see.
Do they dissolve in water? Whoa, maxed out dominoes.
That's what I'm talking about.
These are very maxed out. Okay, so
we
now.
started off with this domino.
Uh-huh.
Then we went bigger.
Yeah.
Bigger,
Yeah.
bigger. And we went to the biggest.
Right.
And this is where we're gonna get the most weight, which is gonna trigger it and release.
Ha ha! Here we go. 3, 2, 1.
Here we go.
The one thing to remember about Rube Goldberg machines is they never work perfectly every time.
Didn't go.
But we tweaked it and adjusted things, and then...
Here we go.
3, 2, 1. Whoa!
Nice. That was pretty far.
Yeah, check this out. Whoop. Okay, so
Nice.
now that we've got the trebuchet firing,
Yep.
and the ball is going over there, we need to get the ball going over here
Yeah.
to
The
cake button.
cake button.
I can't wait for the cake. So I have an idea. Come on.
Okay.
No, wait. Changing direction stuff is over.
Okay.
Now we're gonna talk about tension. What's tension? 1 more than 9 shin. Get it? Because tension and 9 that's okay. Tension is the force that we usually talk about when we think about pulling a rope or a chain or something like that, because you know the old expression, you can't push a rope. But today we are gonna push a rope. I have a rope right here, and I'm going to push it using another force called flexion. I've got some pieces of plastic here, and they bend or flex. And when they do, they want to spring back. But I'm gonna prevent them from springing back by putting them in between these knots. And look, the rope now stays up. And I take another piece, and I stick it on this knot, and then I bend it all the way. This is not terrifying. Really, it's not terrifying at all. Okay, good. And then I take this piece, and I put it here, and I bend it around, and so now we have a rope that's being pushed, and we're defying gravity, and we're making a cool art sculpture. All right, one more here. Ooh, okay, here we go. And flexing. And whoa. Ha-ha! There you go. I've pushed a rope, defied gravity, and made a cool art sculpture. Okay, well, I guess technically I haven't really pushed the rope because we're still pulling from each knot. And I guess I haven't really defied gravity because that one's sitting on the table and all the others are sitting on top of that. But you can't argue that I made a cool art sculpture. Ha-ha! Art! I mean, science.
Sonia and I are maxing out a Rube Goldberg machine. The first part worked pretty well, and now we need to change the ball's direction.
This is a trebuchet. Trebuchet fires the ball, right?
Yeah.
Right now I want to tell you the story of the ball. First, it goes through this fancy film of tin foil.
Aluminum foil?
Right, aluminum foil, because it's, yeah, you're right, it's made of aluminum. It enters this large receptacle.
A garbage can?
You also could be called a garbage can. It falls into this conular device.
Funnel?
A funnel, yes, you could call it a funnel. And then it enters the change-o-direction-o-matic, which is a lever. There's a weight on that end, then it falls off, then the ball goes this way.
Phil?
Or that way.
The one thing you need most of all when making a Rube Goldberg machine is patience.
Ball goes in the funnel, knocks that off, changes direction, and then it goes this way.
Okay.
And that's all I got so far.
So, Not bad.
Yeah.
But we really want to get closer to that way.
Right, because that's the button that gives us cake.
How about we use some chemical energy for this?
Ooh, chemical energy.
I have an idea for this one. Let me go get it.
Go for it.
This is my idea.
Okay.
Ball's actually gonna roll down the tube.
Oh, yeah, because this is a rat trap, right?
Yeah.
Which is like bigger than a mouse trap.
And then it's gonna hit it. Yeah. Nice.
Ooh, so this flips around.
Exactly.
And what's this?
That is something called an antacid tablet. Some water.
And the antacid and the water react. Oh!
It blew. Do you want to test it out?
Sure, can I?
Okay.
Okay, ball comes through this, goes down there, comes out of this, and on the ramp.
Onto the trap.
Oh.
And
Ah, so then
Nice.
it fires up
Yep.
and hits something else
Yeah.
and something button cake. So we got a lot of different energies, but you know what one we're missing?
What?
Is electrical energy.
yeah, you're actually right.
I've got a great idea. Hold on.
All right. Let's see what he comes up with.
This is a chain of beads, and this is glass. Now, if I was to drop the chain of beads, what will happen? It will fall. Yes, that's right. It'll fall because of gravity. But watch this. This side goes up. Why? Because of gravity. Wait a minute. Why does one side go up because of gravity? Well, it gets a little complicated, but I can explain. But I think I'll have to put the beads back in the glass. Okay, so what's going on? Well, when this part of the chain starts falling out, it gets longer and longer, and it has more mass than this side of the chain. And if it has more mass, then it has more inertia. And when it starts yanking out very hard, this side of the chain gets yanked up out of the glass very quickly. And when it gets yanked up hard, it flies into the air. But then, of course, the direction has to change, so it goes around a curve and then goes back down. Because of the speed that it's going, that curve starts lifting up over the top of the glass. And that's how it works. There's a big difference in energy because this chain falls far. I try it from here, and it doesn't work as well. Why? Because the drop from here to here isn't as big. You want lots of force acting on the falling chain, which means the higher you do it from, the better it works. So maybe we should max it out. Yeah. But wait, we should wait for it to stop. And now let's max it out. This is a really long chain, and this is a really long drop. Let's see what happens. Whoa! Look at that! Whoa! Super maxed out! Science!
Sony and I have used potential energy, the lever, and chemical energy.
But you know what one we're missing?
What?
Is electrical energy. Electromagnetism. So watch. The chemical rockets, which we've had from before, they'll fire up, they'll hit the underside of this tray. The marbles will fall and flick this switch. See that sledgehammer?
Uh-huh.
This is an electromagnet, and it will attract the metal in the sledgehammer. Watch this, ready? There. Magnetized, electromagnetism. Now, when the marbles fall, it'll turn the electromagnet off, and the hammer will fall.
Oh, that's pretty cool, actually.
Right?
Can we
So
try it?
let's try it.
Here's something we didn't know. Predicting the flight path of an antacid rocket canister is almost impossible. We had them aim the same way every time. But we stuck with it, and being patient is key, and eventually it worked.
The chemical rockets fire, and they hit the tray. All right!
That's pretty cool.
Yeah, so now we just need hammer hit something, and then something, button, cake.
I have an idea.
All right. Cake any minute now. This is a basketball. It bounces. This is a golf ball. It bounces. But it never bounces as high as where I dropped it from. But watch as I put the golf ball on top of the basketball. Whoa!
Why does the golf ball bounce higher than where I dropped it from? How is this possible?
I only bounced the golf ball from 1 meter high. So what's going on? Well, as the basketball hits the ground, it compresses, storing the potential energy of its bounce, about to give that energy back as it bounces up again. But this energy works as a springboard for the golf ball. And since the golf ball has a lot less mass than the basketball, the upwards kinetic energy of the basketball is given to the golf ball. So, let's max it out. Ball, on a ball, on a ball. 3-ball bounce. Oh, did you see that? Ball, on a ball, on a ball, on a ball. Quadruple ball bounce. Oh, oh. Oh. No, wait. Turns out getting 4 balls to drop straight down on top of each other is pretty difficult. So, we know the mass of the ball is important. Why don't we max it out in a different way? This is a Swiss ball for exercising. It has a lot more mass than a golf ball. So, let's try it out. There you go. The transfer of energy between balls. A great way to lose golf balls.
Sonia has added one more step to our Rube Goldberg machine, a stomp rocket.
It's a hammer rocket.
Exactly.
I like
So
that.
what's going to happen is the hammer is going to hit our bottle, which is going to release all that air that's built up inside of it. It's going to hit that button,
Wait. The rocket hits the button.
and then we get some
Cake!
cake.
Oh, so this is it. So we're done the Rube Goldberg machine with this last step.
Okay.
Do you want to do it?
I think we should do it.
Ready?
Ready?
3, 2, 1.
Let's pause here just before the cake portal's in and recap the science. A marble on top of this ramp has potential energy. As it rolls down, that changes to kinetic energy, which transfers to some stacked dominoes. They fall in a chain reaction, finally causing bigger and bigger dominoes to fall, giving the last domino enough mass to pull a string, attached through some pulleys, to a quick release on a trebuchet. Now, a trebuchet is a first-class lever, with a weight on one side and a sling and a ball on the other. If the weight falls, the sling releases the ball at the right moment and it sails through the air. It's caught in a garbage can and changes directions on a few ramps and another lever as a teeter-totter. Finally, it falls onto a rat trap, which has more energy stored in the tension of the spring. The rat trap smacks another lever, which flips around, turning over some antacid rockets. This allows the antacid to mix with the water and start a chemical reaction that produces carbon dioxide, which eventually builds up enough pressure to fire the container to another lever, which tips, dropping some marbles on a string attached to a switch. That turns off the electricity to our electromagnet. And when an electromagnet doesn't have electricity, it stops being a magnet. So our sledgehammer starts to fall. Now, our sledgehammer is heavy, so it has both mass and speed when it hits this plastic bottle. All that inertia crushes the bottle, reducing its volume. The air gets put under pressure and pushes out through a tube, which takes our stomp rocket with it. The stomp rocket flies through the air and hits our cake button, which then portals in some cake.
Guess we really didn't think that through, huh? The cake should have landed on a table or something.
Would have been nice.
There you go, Science Max Experiments at Large, Rube Goldberg machine. Are you sure you don't want some of this cake?
No, let's
Let's go. Greetings, Science Maximites. My name is Phil. And I am Opposite Phil. Opposite Phil. That's right. Blue lab coat, yellow shirt, evil mustache. I see. Anyway, we're looking at opposing forces today. That's forces that make things go down and forces that make things go up. Right, things with more density and things with less density. Gravity and the opposite, which is anti-gravity. Anti-gravity isn't really a thing. Well, I have to do the opposite. Right. Buoyancy. And buoyancy's opposite, which is girlancy. No, girlancy is not the opposite of buoyancy. You know, you're not helping. Right, not helping. Opposite. Haha. Hello. Goodbye. Hey. Today we're going to be making a gravity-powered boat. Ta-da! It's pretty easy to make. You just put water in the top here. Gravity of the water pushes it out the straw, and the boat goes forward. And it's super easy to make. You only need 4 things.
A piece of styrofoam, a plastic cup, craft stick, and a straw. And the tools you'll need, a pen, a craft knife, and the help of an adult, and science glue.
Which is the same as regular glue, except I only use this glue for science. You take your styrofoam and you cut it into a boat shape. That requires the knife and the help of the adult. Then take your cup and draw the circle that your cup will sit in. And then you want to put 2 slashes with your craft knife in there. Again, get the help of an adult if you need it. And then start carving out the styrofoam with your finger and make a nice little indent just like this for your cup to fit in. See? And then it fits in nice and snug. So then what you want to do is you want to make a hole in the cup. You can use a pencil. The hole has to be just big enough for the straw to fit in. First, you want to take the straw and dig up in this direction so that it will be a nice angle for the water to come out, and then you want to get the straw back up into the cup like that, and then glue it so that it is not going to leak any water. And then in the final step, and this is your choice, you don't have to do this, but you can use your craft stick and you can make a rudder, or if you want, you can make a whole keel, which goes just like that, and it is right in the middle of the boat, and this helps the boat go straight, because sometimes the straw goes off to the side one way or the other. Okay, water-powered boat. Actually, it's a water and gravity-powered boat. You see, what you do is you fill up the cup with water, and the gravity of the water in the cup pushes it out the straw, and the boat goes forward. And this is what it looks like in the water. You fill up the cup, and the gravity pushes the water out that way. The buoyancy of the boat keeps it afloat, and good old Newton's third law, for every action, there's an equal and opposite reaction. The water going out the straw this way pushes the boat that way, and it works pretty well. Whoa, if it's going straight. That's why we have the keel. Okay, so gravity-powered boat. Time to max it out. But first, I need an expert to help me. Oh, of course, Michaela from the Ontario Science Center. Perfect. All right. And let's go. No! I stopped myself. I didn't get wet. Now I'm just gonna get it. No! Hey, Michaela! From the Ontario Science Center, how you doing?
Good, how are you?
That was the best portal malfunction ever! I'm glad you're here, because I need your help maxing out this. The water gravity boat. It's pretty awesome, and what you do is you put the water in the boat, and then it does this, and it propels itself along. So, we're gonna max it out and make it super awesome. So what do you want to do that?
Oh, man, well, what if we just think about making everything bigger?
Okay.
Right? Like, first we're gonna need a bigger container.
Okay, well, that's a good idea. Tell you what, I got my waterproof portal ordering device. So I'll order some sort of a bin?
Yeah.
Like a big plastic bin. Okay, hold on. Hold on. Here it comes. Oh, there it is. Okay, so a big plastic bin.
Yeah, and then, you see this straw here? What if we had something like that, except bigger,
Like a pipe of some sort?
Yeah, like a big pipe.
One pipe coming up.
I need to get myself one of those.
Yeah, but it doesn't always work, so. Oh, here it is.
Wow.
So, bin is the cup.
Yep.
Pipe is the straw.
Yep.
So now all we need is the boat.
Yeah, the platform itself. I think we need something that's going to be really stable because we're going to have a lot of weight this time.
How about like a surfboard or one of those stand-up paddle boards?
Hey, that's a good idea.
Yeah, okay, check this out. Uh-oh,
Oh, no.
water stopping.
That doesn't look good.
I think it might have gotten stuck.
Oh.
We'll have to go get it. Because the water is still running and that might overflow,
Man, it's
so.
stuck somewhere.
Buoyancy is the tendency for things to float. Things like this balloon, or this ball in water. But it doesn't float on its own. The helium is less dense than the air molecules around it, and they fall past the balloon and push it up. The ball is less dense than the water around it. So the water molecules flow around the ball and push it up. This happens because water is a fluid. The particles flow around each other. This works because air is a fluid, and I know what you're thinking. You're thinking, Phil, air isn't a fluid, but it is. Usually we think of fluid as meaning a liquid, but in this case, fluid means anything where the particles can flow around each other, and that includes air. But you know what? It's hard to see the particles in water. Same thing with air. I can say it, but it's really hard to see it. Now this is sand, and it behaves like a fluid too. Well, sort of. Check it out. Look, it's made of a whole bunch of very fine particles, and it takes the shape of its container. But watch this. I put a ball in the sand, and it doesn't float. Now, the ball is less dense than the sand, but it doesn't float because the particles of sand have a little bit too much friction right now. But watch as we move them around and reduce the friction by adding some air. Now, this sand is behaving like a fluid, and the ball floats. Let's see what else floats on sand. How about this pumpkin? Yup, that floats. How about this block of wood? Yep, that floats too. How about this styrofoam ball? Yeah, that definitely floats. Look at that. The sand is a fluid right now because all of the little particles of sand are moving around. But watch this. If I turn off the air, everything freezes in place. Nothing floats anymore because the sand is no longer behaving like a fluid. So there you go, buoyancy. It all depends on the density of the thing and the fluid it's surrounded by. Huh? Science.
Michaela and I are maxing out our gravity-powered boat. We had a bunch of maxed out materials. We just needed to get our surfboard.
So we got our giant bin.
We've got a giant tube. Water's gonna come out of this end.
And we've got a valve here, which means we can fill the bucket, and then we can turn on the valve and see what happens. So, whoa.
Hey.
Okay, you ready?
Yeah.
Now we're gonna turn on the valve, and that means now the water is flowing through.
Ooh.
Hey, it's working.
Not bad.
Right on. Whoa, look at that. This thing is really working.
Yeah, it's taking off now.
So, okay, this is good. It's going about walking speed. Now that it's working, how do we max it out?
Our fuel here is the water, so what if we just had even more water?
And it doesn't last long, does it?
Yeah.
Maxing out our boat even more is easy. A bigger bin for more water, and a wider pipe to move more water for more thrust.
Okay, so a bigger bin
Yeah.
is a lot harder to fill because it's hard to get to the top of the...
Well, you're working against gravity, so it's gonna work for us.
I can really appreciate the amount of water that we're putting into this. That's 4 buckets full.
Wow.
This is 5 buckets.
We open up the valve and it starts to go.
Yep,
Working.
it is working. Look at all the
Wow.
awesome
Check
bubbles.
that out.
Okay,
That works really well.
it really, yeah, it's definitely
Wow.
faster than the other one. I think it's the larger pipe, and we need more water because it doesn't last very long.
Check it out. It looks like it's going even faster now that we've lost a bit of the water.
Less weight.
Yeah.
This is working great, so now how do we make it even better?
Okay, well, the only force working with us right now is gravity, right? Of the water coming out. What if we add in an extra force?
And we could squish the water down to go out faster. Okay, watery high five. Okay, we gotta get it's way over here. Come on, we gotta get it. I want to move the water from this container to this container. Now, I could just pour it, but what if it's too heavy? It's too heavy! Help me, science! Well, science to the rescue with this! A clear plastic tube! Ooh, science-y. Okay, watch this. I'm gonna make a siphon, and it's pretty complicated, so follow along. Are you ready? I stick one end in here, and one end in here! Whoa! Yeah, I know, it's not working yet, but that's because we haven't added the science. First, we need to add a little bit of suction and suck the water through the hose like a straw. It has to go over the highest point. Watch this. And there we go. Look, the water is going up. I can even make the water go up even more, and it still works. But why does the water go up? Water doesn't like to go up, right? Well, the reason why is because there's more water going down than there is going up. So that creates suction on this end, and the gravity of this water pulls that water up. So gravity is doing all the work for us. And that is a siphon. Huh? So now let's max it out. This is the same container of water, but now it's colored slightly blue so you can see it go all the way up through this hose. The only really hard part about this is sucking the water all the way up to there. Okay, here we go. I got it working. Now, the reason why it's working is because there's just a bit more water on this side of the tube than there is on this side of the tube.
With a siphon, it doesn't matter how far you go up, as long as the water on one side is lower than the other.
Science. You know about helium balloons, right? Helium is a harmless gas that is less dense than air, which is why helium floats.
If I was to breathe some helium, my voice sounds higher because helium is less dense than normal air, so my vocal cords vibrate faster. Ah!
But have you ever wondered, is there a gas that's more dense than air? There is.
It's called sulfur hexafluoride, and it's much more dense than air. So if I was to breathe some, my vocal cords would vibrate slower, making my voice lower. Ha 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 ha!
This container is full of sulfur hexafluoride. Ooh, I know, it's invisible, you can't see anything. But watch as I blow some bubbles. The bubbles are floating on top of that layer of sulfur hexafluoride.
The bubbles float because they're full of regular air, which is less dense than the sulfur hexafluoride.
In fact, a balloon will float on this as well. The balloon floats lower because the weight of the latex also drags it down a bit. But the bubbles and the balloons are floating on a sea of sulfur hexafluoride. And it is like a sea because it's a fluid just like water, but it's more dense than regular air.
Science! It's awesome!
Michaela and I are maxing out our gravity-powered boat. It was already working well, but now our idea is to try squishing out the water so it gives the boat more thrust. We just had to come up with a brilliant idea how to do that.
Garbage bag! Garbage bag! Yeah, garbage bag! Okay, maybe we should explain the garbage bag. Okay, so the garbage bag is attached to the pipe at the back end. There's a hole in the garbage bag. Well, we fill the garbage bag with water. Then we tie the garbage bag tight. Tie the knot so the air doesn't get it. Now that we've got that, we use bowling balls! And we put the bowling balls on top of the garbage bag, and this will, whoa, squish the water out.
Really, it's pushing on that bag.
Okay, ready? Okay, let's see.
Hey, it's moving.
It is
Our bowling balls were squishing the water out, but the boat didn't seem to be moving much faster.
I think the bowling balls made the whole thing too heavy.
What if we raise the bin up?
If it's higher up, then there would be more force due to gravity.
Yeah, so we have the bin on like stilts or something,
Oh my God.
and then it has to fall further and then maybe the water's going faster.
I love that idea.
Okay, good.
Yeah, let's try it.
So what we need to do is get
Wait,
this. Oh, I thought this was the shallow
No,
pool.
yeah, no, that's
no, that
over
one's,
there.
that's that
yeah,
one. Yeah.
not here.
Max Historica.
Long, long ago, in the time of ancient Greece, there lived a genius named Archimedes. One day he was in the tub and he noticed something.
Oh, hello. Look at that. When I get into the tub, the water level goes up, and when I get out of the tub, the water level goes down. Ha ha! Eureka!
I, don't get it.
Well, I can calculate how much volume something takes up by how much water it displaces.
Yep, still not with you.
Now, I'll give you an example. How much water would be displaced, pushed aside, if I put this ball in the water?
It's light, so not much.
Ah, it doesn't matter how heavy it is. It only matters how much space it takes up. Watch. Ha! You see? The same volume, huh?
I think I see.
How much water will be displaced when I put this bowling ball in?
More because it's heavier.
Ah, nope. It doesn't matter how heavy it is. It only matters how much space it takes up. Watch.
Oh.
You see? A simple and easy way to measure something's volume.
Archimedes, one of the greatest and cleanest scientists in history. Join us next time for more Max Historica. The metric system in 60 seconds.
The metric system is a way of measuring things. Water boils at 100 degrees Celsius, a kilometer is 1,000 meters, but few people realize just how interconnected the metric system is. First of all, it breaks down to a base 10 system. Everything is 10, 100, or 1,000 of everything else, and it's all based on water. This is exactly 1 liter of water. It weighs exactly 1 kilogram. It fits into a cube 10 centimeters on each side. It boils at 100 degrees Celsius and freezes at 0. And this happy little fellow is 1 milliliter. It fits into a cube 1 centimeter on every side. It weighs exactly 1 gram, and the amount of energy required to raise this 1 degree Celsius is 1 calorie. The metric system, everything interconnected and all based on water. Ha! Oh. Uh-oh.
Michaela and I are experimenting on our maxed out gravity-powered boat. Trying to squish the water out with bowling balls added too much weight for it to make much of a difference. So now we've raised our tote higher up, which means the water will have farther to fall and be going faster when it comes out.
And I got a totally awesome name for our boat.
Tell me, what's up?
Totes McBoats.
That's a totally awesome name!
Totes McBoats? Yes! Okay, so are we ready to fire up Totes McBoats?
That's right, yep.
Okay, I'm gonna turn on the valve. Okay, ready? And let go. Totes McBoats!
What we hadn't considered is that much weight that high up would be tippy.
Totes McBoats no longer afloats.
We needed a way to solve the tipping problem first.
You know what we need to do?
What?
We need to build an outrigger.
All right, so check it out. This time we have an outrigger, which means our boat's gonna be a whole lot more stable. It's not gonna fall that way because this thing is floating, and it's not gonna fall this way because it has a lot of mass as well. I think we're almost ready, eh, Phil?
Yeah. Okay, are you ready?
Ready?
Okay, let's do it. Turn on the valve.
Here we go.
Go, Totes McBoats! Oh, yeah! Yes! Yes! Totes McBoats! Oh, the outrigger's pulling it to the side. Oh, in this way. Yes! It goes really fast.
Our gravity-powered water boat worked great. The water ran down from high up, giving it more speed due to gravity, but no more mass than before. And our outrigger kept the whole thing from tipping over. Totes McBoats was a success.
Thank you very much, Science Max Experiments at Large, gravity-powered boat, otherwise known as Totes McBoats! Totes, go